So maybe you should remember that the point is that in that case, the difference with respect to the implicit model was in the evolution equation. R is the internal variable whose evolution now is given explicitly as an evolution equation in terms of the free variable, the strains, and the internal variable itself. Okay? This corresponds to the norm of the strains we have chosen. We saw some alternative for that. And then the goal of this, which is a first order differential ordinary equation, is to obtain the value of R at every time t, or at the current time t, with information on previous times. So we have at times s belonging to the interval 0, assuming 0 is the initial time, t the current time, we have all the information we need. We have been able to, in a sequential advancing method of integration, we have been able to compute and record all the information, typically the strains at previous time step. Okay? Assuming that we are able to integrate this solution analytically, that's one possibility, then we'll have a function RT that provides for every t the solution for R. So for every epsilon, and in particular for the epsilon at time t, we will know R. If we know R just by replacing in algebraic equations, we obtain Q, the Hartree softening variable. By replacing it here, we will obtain the damage variable, and by replacing into this equation, then we will obtain the stresses in terms of the strains, and by multiplying the elastic constitutive modulus C times epsilon, this would be the elastic stresses, the effective stresses, and by multiplying by the factor 1 minus d, we will obtain the damage stresses, the physical stresses. Okay? Well, the point is that, as I told you, not always, in fact, almost never, or never for practical purposes, we are able to do that, to compute, to integrate this first order ordinary differential equation in an analytical manner. So we are resorting to numerical integration. We know that numerical integration in general is an approximative integration. We never will obtain the result, the exact result, but it will be enough for us to get a result which is as exact, as accurate as we wish in terms of the time step. What is the time step issue? Well, we just discretize in time, sometimes it's called discretization in time, the interval of interest in a number of subintervals. They could be of the same length or of different length, but in principle, normally, they are considered of the same length. So that these subintervals, every one containing the first time and the last time of the subinterval, Tn plus 1, the union of those subintervals is exactly the interval of interest, 0 capital T. The length of the interval is the difference of the end interval minus the initial interval for the subinterval, initial time for the subinterval, and that delta T is called the time increment. And then we have to imagine, we have to resort to some procedure that allows us to obtaining the value at time n plus 1, that would be the current time, in terms of something, the values of the variable we want to integrate in previous times. Okay? And we saw also one way, specifically how this could be done in the case of the implicit models. And we saw that in that case, the solution was a closed form solution. So a solution that just didn't involve explicitly the delta t time. Okay? This is not the case in general, and we'll see now how would you manage this problem in this case, which is the viscosity case, the viscous case. We have eta different from 0. Okay? Well, then we are using, in this case, maybe the most popular method for integration, this first order differential equation is the so-called alpha method. The alpha method is very simple to understand. I'm just going to, maybe some of you are already familiar with it. The concept is the following. Let's consider the current time step. So we are just to solve, we're at the time step Tn plus 1. So at Tn, we know everything we need. And at Tn plus 1, we just know some of the information that we need for integration, but part of the information is unknown. In other words, at Tn, for instance, we know xn, and at Tn plus 1, we want to know the value xn plus 1, okay? Fulfilling this equation. Not exactly maybe, but approximatively in such a way that as delta t tends to 0, we just approach more of the error, the committed error is lesser and lesser. Okay, let's use some notation. For instance, the value of x at the initial of the time step, Tn, let's call it xn. The value at the end, it's called xn plus 1. And now let's consider a generic time inside the interval, the current time interval. Let's call the time, one time here, Tn plus alpha. Why alpha? Well, let's consider that this time, if this length of time is delta t, this time is alpha delta t. So a fraction of the total length of interest, of the time step. So alpha, logically, going from 0 to 1. For alpha equals 0, I will be here. For alpha equal 1, will be here. So I'm parametrizing, in terms of alpha, the axis t. Okay? And now, let's do something which is approximative, an approximation. So let's parameterize also the solution in the interval xn n plus 1 in terms of the same parameter. So let's say that the solution corresponding at Tn plus alpha is just the linear interpolation of the solution xn and the solution xn plus 1. The linear interpolation. Okay? So we write xn plus alpha as 1 minus alpha times xn plus alpha times xn plus 1. So then I'm assuming that the solution, starting here and taking this final value, in between, maybe the reality, the real solution, is not a linear variation, but I'm assuming that linear variation. Okay? In the spirit that as the time step is smaller, I'm approaching the real value of the solution. Okay? Look that, for instance, for alpha equals 0, this term drops, and then xn plus alpha equal xn, so I'm here. For alpha equal 1, this term drops, this 1, so I am recovering that. And in between, I assume, that's an assumption, and the assumption involves errors, or loss of accuracy, so then I have a linear approximation as main hypothesis of this method. Okay, and then what I'm going to do in the, what is done in the, typically in the alpha method. In that equation, I approach this x dot as the slope of this curve. The slope of this curve that I have supposed constant, according to that. So this slope is very easy to compute. This difference be divided by this difference. So x dot n plus 1 is xn plus 1 minus xn divided by delta t. Is that the slope? Okay? So this is just for the left-hand side. What about the right-hand side? Here I don't have any time differentiation. Look that the equation is always have a time differentiation at the left-hand side and something which is not involved in time differentiation at the right-hand side. That is the type of equations where alpha method are typically used. Okay? So then I replace x, whenever x is in here, whatever it is the x, by the evaluation of x at a certain point of the interval. So I'm free to select what here that's fixed, you know, that's the slope. So this is this value, this increment divided by this increment here. But as for the right-hand side, I just replace x and t by some values of this straight line. Okay? So we have different options, and for any of these different options, I should expect having different solutions. Okay? So for instance, what if alpha in that expression, alpha is 0? So this, at the right-hand side, the function f is evaluated at times xn. Okay? So I said that this is constant, and then at the right-hand side, I put the value of the function at xn. Okay? So look, for that, if this is xn, then it's clear that, well, that is called the forward Euler or explicit scheme. Explicit is synonymous in many aspects of computational mechanics as something that can be done without much computational effort at the cost of some error. Okay? So what does that mean? That, look, now if I place here the values of f up tn, these already know, because everything I'm supposed that I know xn, so I can replace here, this is known, the right hand side is known in advance. And then from this equation I can just solve for xn plus 1 in a trivial manner. Okay? That is maybe the simplest way of doing it, maybe also the less accurate. That's called, for alpha equals 0, evaluation of the right hand side at the initial of the time step is called the explicit or also forward Euler scheme. On the other hand, I could evaluate that, for instance, at this point. So this corresponds to alpha equal 1. Alpha equal 1 returns this time, and then I'm replacing in here the value of f at xn plus 1. So, by doing that, then I will have some equation I have to solve. That is not clear, because now I don't know this xn plus 1. Xn plus 1, I have xn plus 1 here, I have xn plus 1 here, I can have a nonlinear or linear, whatever, equation. I have to solve this equation and find xn plus alpha. It's computationally costly, more difficult, but we will see that it's more accurate. And then we can take any alpha of that, in fact. Specifically, sorry, I forgot to say that this, when we put or evaluate the right-hand side of the equation at the end of the intertime interval, this is called the backward Euler or implicit scheme. Implicit is a word that, again, in computational mechanics, is somehow associated to extra computational cost, to decrease, to minimize the computational error. Okay, so we have the two limits, and here there are another option, which is what is quite used, which is called the Crank-Nicolson scheme, or midpoint rule. Why midpoint rule? Well, because we just evaluate the right-hand side of the equation at the midpoint of the time interval. So this is for alpha equal 0.5. Okay, so we have these options, and of course we have different options. And in fact, you will be requested in the assignment to compute that for different to do this exercise, to see what happens using different options for the integration. Okay? Okay, so this is for the alpha method. That is general. Let's apply this alpha method to the problem that we want to solve, which is the integration. So now R is x, and here epsilon is the variable that drives the problem, and R is the result I want to take. So that's the equation. That's the alpha method. That's the equation I want to solve. Initially, we need some initial value of the variable to be integrated at the initiation of the analysis. So we know that R initially is not 0, is the threshold that we have defined, and you remember maybe that it was the ultimate, the elastic limit divided by the square root of the Young modulus. We identified that in the last lesson. Okay, so what do we know? You know, this initial value at t0, in this case is E0 times 0, the initial of the period of interest. And then we know, typically, we just need to know the value of r at the initial of the time step, at the initiation of the time step, Rn. And of course, we know epsilon. Epsilon is a driven variable. So epsilon, we know everywhere we need. It's something that just supposed that is a data that enters into the integration problem. So in particular, we know epsilon at the end, at the beginning of the time step, and we are supposed to know epsilon at the end of the time step, n plus 1. And of course, if we know epsilon, we can also know the norms which are obtained. We'll see that in detail later on, that these norms can be computed as a function of epsilon. So we can compute tau epsilon at n and tau epsilon at time n plus 1. So what are the norms? Well, we want to integrate that and obtain r at the end of the time step. So that in the next time step, this r will be Rn. And then, once we know r, just by substitution, we'll obtain q, the subscattering isosceles variables, just by algebraic replacement, and then from that we can obtain d, and from d we can obtain sigma. So everything else, once we know r, is just done by substituting into algebraic equations. So let's do that using the alpha method. R dot would be now obtained as the increment of r, Rn plus 1 minus Rn, divided by increment of t, the same we have here. Now x plays the role of r. And then at the right-hand side, which is now replaced by this Macaulay bracket. You remember the Macaulay bracket is a function that returns the same value inside of the bracket for positive values and 0 for negative values. So just cuts off the negative values. So then we replace that just in a certain value, tau epsilon and r, in a certain time inside the time interval. So tau epsilon n plus alpha means that we are evaluating tau epsilon at time tau n plus alpha, and tau r n plus alpha is the value of r at this time n plus alpha. Where? We'll see. But at the interior of the time step. And now we do the parameterization or the interpolation as we did here. We just interpolate the solutions of that, assuming a linear variation in terms of t. So we said that tau epsilon n plus alpha is 1 minus alpha tau epsilon at n plus alpha tau epsilon at n plus 1. That we know. This is something that we know. That's the data, because I know that and I can compute that. That's something which is now known, and since alpha, so this can be known. Second, Rn plus alpha. Rn plus alpha is what we showed before. I just interpolating Rn plus alpha in that way also. So 1 minus alpha Rn plus alpha Rn plus 1. Okay? Or maybe some of you could consider the possibility of, instead of interpolating tau epsilon, computing epsilon n plus alpha and then replacing and computing tau. Doesn't worth it. Okay? So if you, of course, we commit an error as we linearize that, but this doesn't increases the error. Okay, so I mean, we just interpolate both tau epsilon and r in terms of alpha. Again, for alpha equals 0, we obtain the values at the beginning of the interval. For alpha equal 1, we obtain the values at the end of the interval. And for intermediate values of alpha, we obtain intermediate values.